Hi, welcome to this video on the atomic structure for AP Chemistry. So we're going to start off just with a quick overview of our periodic table. So as we know, our periodic table are composed of elements. So each individual element has its own unique properties. And so therefore they have important things that we're being told by looking at our periodic table. So first off, when we look at the element symbols on our periodic table, the number right above it is called the atomic number. That's our number of protons. Protons are unique to each individual element. Our elements on our periodic table are actually organized neatly for a purpose. So all of my elements that I find on the left side of my periodic table, those are considered metals. So anything like mobidium or chromium or cesium, those are ones that we wouldn't know probably as metals. You know, you probably realize copper and aluminum and those ones fit into the metal category. But they have those metal properties of being malleable and ductile, which means that they are bendable and can be stretched and they are shiny. And then the other really important thing is just to remember that your metals are losers of electrons. So they tend to give up electrons very easily, and that forms positive ions, which is really important for ionic bonding. We also have metallic bonding, which are just samples of pure metals. So if I have, it doesn't even have to be pure, it could be a mixture of metals like an alloy. But when we have metals that bond to other metals, that's through metallic bonding, and that's because they have the mobile electrons that can flow amongst all of the electron clouds of those when that metallic bond is occurring. On the right-hand side, we also have our nonmetals. On the nonmetal side, the general properties of our nonmetals, they're going to be dull, they're going to be more brittle if they're solid. They typically, most of them are gases, but they can be solids and liquids. So for example, sulfur is a solid, bromine is a liquid. They can form ionic bonds by gaining electrons and becoming negatively charged, and that allows them to form a positive-negative attraction with to make an ionic compound. We also know that our nonmetals can bond with each other by sharing electrons in a covalent bond. All right. On our periodic table, just in general things you want to know, just remember when we use the term group or family, we're talking about the vertical columns. And so we can divide those up into groups A or B. When you say like 1A, you're talking about the representative elements, which are typically going to be your S and your P block or S and P elements. And then the B are the transition elements in the middle. And then we say periods, we're referring to the rows across. So our periods are usually numbered down the left-hand side of the periodic table. You do want to make sure that you know the name of the metals. So group 1 or 1A is going to be the alkali metals. And then you've got alkaline earth metals in group 2. The other important ones, the halogens, are in group 7A or 7, Roman numeral 7A. And then the noble gases are the rarest, and those are going to be in group 18 or 8A. So typically in the more modern periodic tables, you'll see it numbered 1 all the way through 18 across. But just be aware the A's work as well. So you want to make sure you memorize what those different groups are on your periodic table. All right, so we're going to talk a little bit about some of the early theories and experiments that allowed us to develop the atom over time. So initially we start off with the postulates of Dalton, which led to the atomic theory of matter. So at that time, there just wasn't the availability of experimentation to see atoms. So his theory is based on what he believed. So one is that all matter is made up of atoms. So they thought of those atoms as like the building blocks. So there's nothing smaller, and they were indestructible at the time. And then all atoms of a given element are identical in both weight and chemical properties. So what that means is if I have 5 atoms of carbon, they're all going to be exactly the same as what they thought at the time. And then compounds could be formed by combining atoms together. And so then they expanded on that and said, well, when I start with two elements and I make something that I think looks new, it's really a combination of those elements chemically. So when we rearrange our atoms, we can make new elements or new compounds, not new elements, sorry. The two modifications to Dalton's theory that we know have occurred over time as we've learned more. One is the subatomic particles were discovered. So we discovered that there are protons and neutrons and electrons within the atom. And then we also discovered that isotopes exist. So while all atoms of a given element are going to have the same chemical properties, their weights are not going to be the same because of the different numbers of neutrons that isotopes can have. So we could have 5 atoms of carbon and they chemically would be the same, but they may be different isotopes. One of them may be carbon-12, another one may be carbon-14. Then we have Avogadro's hypothesis. Really, Avogadro contributed quite a bit to our gas law chapter, so we'll talk about him a little more. But one of the things that's really important with him about the atoms is he's one of the first people to give us the ability to count atoms. Because they are so small, we can't individually count them. So what he did was he was studying volumes of gases, and so he found that different gases, when he had equal volumes of them, they actually had the same quantity of overall particles, atoms or molecules, whichever one it was. So that's led to Avogadro's number, which we know we use to count our number of particles. So looking at our first subatomic particle that was discovered, that would be J.J. Thomson with his discovery of the electron. So J.J. Thomson basically applied a high voltage to an evacuated tube, which he called a cathode ray tube. And so what he found was that the cathode ray that was produced when he had a gas within that tube is as he applied the electrical voltage to it, the ray that was produced, it was produced at the negative electrode and was going towards the positive electrode. But then he noticed that it was being repelled by the electric field. So this led him think that this negative electrode was pushing away negative particles, because we know negatives do not like other negatives. So basically, Thomson discovered that all atoms contained these negative particles that were pushing away from the negative electrode, and so he called those atoms the electrons. So all atoms were, so if we look right here, we can see that Thomson discovered he could repeat the deflection in calculation using electrodes of different metals, so it worked with different elements, and all metals contained electrons, and all atoms contained the electrons. So furthermore, all atoms are neutral. There must be some positive charge within there, so that negative charge must be balanced, otherwise our neutral atom wouldn't exist. So that's where the plum pudding model came from. So a lot of times you'll see, instead of this plum pudding look model that we have over here, a lot of times you'll see them put like a big positive in here, because what they basically at the time thought was there had to be positive balancing that negative, and they weren't really sure. They thought it was all evenly distributed throughout. We also had, around that same time, Robert Millikan studying the electrons as well, and he was able to use his famous oil drop experiment to determine the mass of an electron, which will be important later, is 9.11 times 10 to the negative 31 kilograms. So keep in mind that negative 31 exponent means electrons are very, very tiny. Continuing the study of our particles, we had radioactivity. So Henri Becquerel was French, and so by accident, he put a piece of mineral which had uranium in it next to a photographic plate, and what he found was that it basically darkened the photographic plate. And so he was like, oh, wow, this must be radioactive. And so he knew there was some sort of emission. So he coined the term radioactive for us. And so he just said that this emission of radiation coming from that mineral must be considered radioactive. At the time, they didn't even know that was not unsafe, though, so they were still messing around with it. So you had 3 types of radioactive emissions. You had alpha, beta, and gamma, that they were discovered over time. So alpha is are weaker of the three. So when we are exposed to an alpha particle, they're very large. Alpha particles are the size of a helium atom with a mass of 4, 2 protons. So they consider them, because they're so large, to be very slow moving. So they don't consider them to have a high penetrating power against like skin and things like that. Beta particles are a little bit faster. They are kind of like a high-speed electron because they do not have a mass. And they have a negative overall charge. They're a little bit more harmful, have a higher penetrating power. Gamma waves and gamma rays are what we consider to be the most dangerous of our radiation particles. It's not an actual particle itself, it's just pure energy. It's part of our electromagnetic spectrum. So when we are exposed to gamma rays, we are very concerned because that is a high penetrating because of the high energy that it exists at. Then we have the nuclear atom. So up until this time, 1911, we thought that only electrons existed. The nuclear atom was when was discovered by Ernest Rutherford. Basically, Ernest Rutherford did his famous gold foil experiment. So when he aimed some alpha particles, which are positively charged, towards some gold foil, he thought that that gold foil would just pass straight through, or that alpha particle would pass straight through the gold foil, because your positive would be attracted to your negative, and he thought it would go straight through, just like you see in this picture down here in the bottom right. So that's what he expected to see. However, when he did pass them through, what he saw was that there was these little deflections of ones that were deflecting off in other directions. So that led him to believe that there was something positively charged down here in the center, which he then decided was a nucleus, or a dense positive core, and that the remaining portion of the atom was going to be mostly empty space, and so that was where your positive charge was actually like located. So Rutherford's experiment has actually led us to the modern view of the atomic structure. And so even though he didn't really discover the proton itself, he eventually did later, but initially his experiments led to the just discovery of the nucleus itself, and the fact that we now know atoms, we consider those the smallest particles of an element that are retaining its whole chemical property. So we updated Dalton's theory. So while we do know now that there are protons, neutrons, and electrons within our overall atom, we know that the atom itself is the smallest particle that's still going to have the properties of the elements. So within our nucleus, we find our protons and our neutrons, and then the electrons are located outside of that nucleus. Electrons are located in what we call the electron cloud, but notice how much smaller the nucleus, the dense nucleus, is compared to the full electron cloud. However, the protons within the nucleus protons and neutrons is where all of our mass is coming from. So that is a lot of mass in a really small volume. So that makes the whole nucleus portion very, very, very dense. We have our positive protons and our negative or neutral neutrons. They have no charge. And then electrons are very, very small compared to protons and neutrons. And so therefore they have really tiny masses compared to them as well. One thing you're going to notice, this is a little different than what we would normally say, and we don't really go into this in first year chemistry, but you will notice that we use letters, the Z for atomic number and the A for mass number. The atomic number comes from your number of protons. And so if elements are the same, then they should have the same number of protons. The mass number is the number of protons and neutrons that are found within the nucleus. So if they have different mass numbers, it means they're isotopes of each other. So this should all be somewhat familiar. So when we write our isotopic symbol, we will write our mass number on top with our atomic number on bottom next to the element symbol. And that must be written on the left-hand side. That's the correct way to do it. Another thing you'll notice over here on the left is when we are really talking about the actual mass numbers of these atoms, okay, the mass number of an electron is 9.11 times 10 to the negative 31. Remember, Robert Millikan figured that out. And so then you can see the proton and neutron masses are relatively the same, but also still very, very tiny. So we typically make the mass numbers relative mass numbers. So when we say that the number of protons is 3, so our mass number for that is 3 AMUs, those are atomic mass units. It's not actually in kilograms. It's just that the protons and neutrons are equivocally the same. So we're going to go ahead and count them equal to each other and make it a nice friendlier number. The actual mass, if we were to add up all of the mass of the protons and the neutrons and the electrons, is not a whole number. That's because of mass defect, which we'll talk a little bit later, but it really has to do with binding energy. It's because some of that energy is stored in mass, going back to Einstein with his E equals mc squared. So some of that energy that's holding the protons and the neutrons and the electrons together within the atom actually has some of its mass located in there. All right, so let's talk really quick about writing the symbols for our atoms. So this is just a quick review. So when we write our symbols, so write the symbol for the atom that has atomic number of 9 and a mass of 19. So you would look on your periodic table, and on your periodic table you would see that the atomic number of 9 is 9 protons, so that's going to be fluorine. So you would write an F. And then it has a mass number of 19, so that would go up on top. And your atomic number goes down on bottom as a 9. So how many electrons and how many neutrons does it have? So we know that if the atom is neutral, so it's not an ion, our protons have to equal our number of electrons because the positive and negatives have to balance out. So that's why we would have 9 protons, we would have 9 electrons, and our number of neutrons. So the other important one we want to remember is protons plus neutrons have to equal, that is a P, but I know it doesn't look like it, the mass number. So when we're adding all those up, we would see that 19, so if this is 9, this has to be 10 to equal 19. So we have to have 10 neutrons and 9 electrons. All right, so that should be just a quick review, so that should be pretty easy for you. All right, and then you also have isotopes. I know we talked about those briefly. So those are atoms that have the same atomic number, so they're the same element chemically. All those elements that are isotopes would not be treated any differently. Most elements have at least 2 stable isotopes. There are just a few that only have 1 isotope, but for the most part, every element has more than 1. Hydrogen's isotopes have special names. So if we're just talking about hydrogen 1, that is going to be 0 neutrons. And so we just call that regular hydrogen. But hydrogen with a mass of 2, so let me see if I put this here for you. So if we just have hydrogen atom, which is hydrogen with a mass of 1, and then we have deuterium, which is hydrogen with a mass of 2, and then tritium which is hydrogen with a mass of 3. So the more neutrons we have, obviously deuterium is 2, tri is for 3. But basically your isotopes are just varying quantities of those, and it has to do with stability. We'll talk about it briefly in class, but it's really about the nuclear stability, and that's really the only difference. Okay, so last thing is ions. So we have atoms, which are our neutral element particle. We can also have ions. Ions are when we have charged element particles. So these are going to be formed when the electrons are lost or gained in ordinary chemical reactions. It does change the size of them, which we'll talk about during our periodic trends section a little bit later. But when you should remember that you have cations and anions. A cation is the positive ion. So I try to always remind y'all the cation, you got your metals. So your metals are typically going to be your cations. This doesn't come out as cute whenever I'm doing this on here, but your metals make your positive cations. So that's your little M for its ears. So they lose electrons and become the positively charged. Your anions are going to be your non-metals. Those are typically going to gain to get to 8 valence electrons overall, and they become negatively charged. We also have polyatomic ions, which you should have memorized, hopefully. And those are going to be actual covalent units of atoms, but because their whole unit works by the gain or loss of electrons, they're either deficient or have an extra, so therefore they get a positive or negative charge as well. All right, so if we wanted to write the nuclear notation for each of the following atoms or ions, you would basically do what we just did. So which atom has 12 protons? So we'd have to look on our periodic table for which element has 12 protons. So 12 protons, when you look at it, is magnesium. So that's going to be, oops, I thought I had my thing on, is going to be Mg. And then we have 13 neutrons. So if I add those together, that's going to give me 25 as my mass number. So I'm going to put that on top. And if I have 10 electrons, I'm going to put 12 on the bottom. Then the other thing to pay really close attention to is this is an ion. The reason I know it's an ion is because I got 12 protons and I got 10 electrons. So when I'm looking at this, that means I have a +2 charge. Hopefully that you recognize that. So when you're writing an ion, you put your charge up on the upper right. Now, I always do my positive first, but a lot of people will write it the other way and do 2+. It's just how you learned it. It doesn't really make a difference one way or the other. All right, on my next one, I have 15 protons. So what element has 15 protons? You look on your periodic table, you'll see that that is going to be phosphorus that has 15 protons. All right, so we would write a P here. And then we see 17 neutrons. So 15 and 17 is, if I make a mistake on this, 32. You can totally make fun of me in class. All right, so I got 32. And then I'm going to put it over 15 for the atomic number. And then I look and I check and I see that I've got 15 protons, 15 electrons. So that is electrically neutral. So where this one is an ion, this one is an atom. So those are important definitions to make sure you understand the difference. All right, so take a few minutes and I want you to work the others. So go ahead and pause and then come back to them and see, and hit play and see if you get them correct. All right, so on this one, 8 protons, it's going to be oxygen, and we're going to have 17 over 8. And then when we compare protons to electrons, I'm going to have a -2 overall charge. So that's an ion. So oxygen, -2 ion. 55 protons. That's going to be cesium. So 55 protons. That's going to be cesium, Cs. So 55, 54, that's going to be 109. So I'm going to do 109. If I did my math wrong, just pretend I did it correctly. Oh, duh, I didn't do it right, did I? 1 second, let me erase that. Because I need to add my protons and my neutrons together. And they tricked me by switching it up. So 55 protons and 75 neutrons. That's going to be 130. Hopefully that is correct. 130. And that means 55 protons are going to go on the bottom. All right, and then when we look at our protons versus our electron quantities, we're going to compare proton, electron. I've got 1 more proton, so that's going to be a +1 ion in this case. All right, so hopefully you understand how to write the atomic symbols, and that was a good review over the charges and how we're finding positives versus negatives, because we're going to need those later. All right, so continue on if you want to the next section, which is electrons and reviewing over electron configurations. But for this one, you should just know a basic overview, periodic table, the atomic history, and then how to find the important pieces of the atom and ion information that you're going to need for bonding.